Hi, good morning and good evening, everyone. Today we are very honored to have our valuable guest, Dr. Haohan Wang from CMU. Uh, Let me briefly introduce Dr. Wang. Haohan is an incoming assistant professor at Two School of Information Science at UIUC. His research focuses on trustworthy AI and computation biology and healthcare, covering a wide spectrum of topics such as computer vision, NLP, and statistics. He recently graduated from CMU, where he works with Professor Eric Xing. He was recognized as the next generation of biomedicine from the Broad Institute of MIT and Harvard, and a rising star from Baidu Research. Let's again sincerely welcome Dr. Wang to give us his talk towards a principal understanding of robust machine learning method and its connection to multiple aspects. Let's welcome him.
Thank you very much for the introduction and of course the invitation, and also thanks to everyone for being here today. So today I'm going to share this talk entitled Toward a Principled Understanding of Robust Machine Learning Methods, as well as its connection to multiple aspects. Okay, so for this talk is organized as following, and first we will talk a little bit about the setup of the challenge of robust machine learning, and also our hypothesis that why some machine learnings are not robust enough. And then in the middle part, which will be the main topic today, that I will introduce some of our recent work about the principled understanding of robust machine learning methods, where we kind of gave the main result a very cool name. And also I will discuss briefly about its connections to some of the empirical method development. And then the last part of this talk will be about how we can leverage this principled understanding to introduce almost as a labor-free manner, new methods for robust machine learning. Okay, so let's get started with the first part, the hypothesis about robust machine learning. So let's look at the positive side first. So our community has made significant achievements about machine learning, especially like maybe in image classification. And this figure shows that the increment of prediction accuracies over all kinds of models over the standard ImageNet benchmark. And because of this rising performance, the media starts to make all kinds of titles saying that, okay, deep learning might outperform human in these image recognition tasks, and maybe it soon will take place our jobs. Okay, however, maybe we need to, as the researcher of deep learning, we need to look a little deeper than those titles. And for example, in one of our early stage work, we try to argue that the pursuing about those ImageNet SOTA leaderboards might not be very fruitful down the road. And we try to make that argument by showing some primary labels of those samples. And if someone is interested, maybe we can try to guess what those primary labels associated with these samples. So the first one is a flute, and the second one is a comic book. The third one is actually labeled as those two animals, and the last one is probably the hardest one. It's labeled as sunglass. So basically, we use this evidence to show that despite the very high performing leaderboard numerical results, the model might actually learn something else instead of how a human recognizes those images. And recently, the community proposed several more evidence to support that argument that behind the very high numerical numbers of the leaderboards, that there are actually some challenges of image classification. For example, these two evidence shows that there is a tendency of those convolutional neural networks in superficial statistics. The above example shows that the ImageNet trained convolutional neural networks are biased towards some texture. And the bottom one is probably more popular, very well known as adversarial examples. It basically tells the story that we can construct some carefully corrupted noise and adding those noise to the image, and the result in the image will successfully deceive the model to predict the image to be something else. This basically tells us that despite the model can get very good predictive performance on those benchmarks, it may not understand the image as well as human, or at least in a way that human does. So in our work, we try to ask that why a model behaves in this way. And to answer that, we propose this hypothesis that the reason for the non-robust behaviors of those machine learning models lies in the data. For example, when we collect the data to train the machine learning models, within the data, there are some semantic features that we hope the model to learn, and it's usually associated with the label that by the definition of the nature of a human. So however, within the data set, there are also some other features that are coincidentally correlated with those semantic features. And in this work, we just named them superficial features. Of course, one can also call them like spurious features or confounding factors. And because of those correlation, there will be some association between the label and the superficial features. And then when a model is trained to optimize a vanilla loss, it cannot really differentiate these two sorts of features, and it may learn a combination of both, resulting in some unintuitive behaviors. So this is our core hypothesis of why a model is not robust enough, and will serve as the ground of the following work in this talk. And so first, let's see some evidence to support this hypothesis. The community has noticed several reasons that why the models behave with that tendency in superficial statistics. For example, for the above line, this paper shows that the origins of the texture pairs are actually in the data. And at the bottom, when there is a corresponding, also very popular example, basically shows that for the challenge of adversarial examples, the answer lies also in the data. And we also have our own example to offer more evidence in that argument. So basically, we test the images of image classification. Basically, we grab an image and use Fourier transform to map the image into its frequency domain. And then with a predetermined radius, we can cut the image into low frequency and high frequency counterparts. And then we can reconstruct those images from each of those frequency components. And then together with the original image, we fit these three images to the original model trained on the original images. And here we can see that while the model can predict the original image correctly, it predicts the low frequency reconstruct the image to be something else, and the high frequency image to the correct label again. And of course, to a human, the low frequency reconstructed image probably look more similar to the original image. And in case someone is interested in to see this, this is the pixel value rescaled to from 0 to 255 scale for the high frequency image. It's still a bunch of noises in my opinion, but the model somehow make the correct prediction. And this does not happen to every image. Across the standard CFR10 test dataset, we identify like 500 to 600 images that have this kind of behavior. And we consider that significant enough to raise an alarm with the message that although the model can do a pretty well job in prediction accuracy, it does not necessarily understand the image as well as a human does, or at least in the manner as a human does. Okay, and in addition to this evidence, this is probably also one of the most famous examples to show that despite the prediction accuracy, the model may exploit some features that are not considered useful by the human. For example, in this 2016 paper, which is probably one of the pioneers in this field, they show that in dog versus wolf classification, the model might learn to use the background of snow to classify wolf. And I hope this evidence accumulated together could support our hypothesis about why the model does not perform very robust when it tests in the real world manner. And so in this talk, we will focus essentially on this problem. And just to make the terminology clear, for the rest of this talk, we will refer to these features as superficial features. And of course, by choice, one can choose to call them spurious features or confounding factors as one wants. And also basically this talk is going to be about how to train those robust models by countering these superficial features. Okay, so here is the first part about the background and the setup of the hypothesis of robust machine learning. And then let's look at basically the main message of this talk, the principled understanding. So to do that, let's first introduce a little bit more about the setup of this talk. So since we talk about robustness, in this talk, we will talk several different scenarios regarding robustness, and here list a couple of them, namely the domain adaptation or its later extension called domain generalization, or some more recent setups. So here is basically a brief recap. Domain adaptation talks about the scenario where we train a model on a collection of data, the source domain, and then test the model on some other collection of data, the target domain. And during training in domain adaptation study, we usually leverage the samples either labeled or unlabeled data from the test domain. And that domain adaptation is going to serve as the theoretical scope of this talk. Later, we will offer a new generalization error bound of domain adaptation. And despite the popularity of domain adaptation, people argue that maybe it's not realistic enough. Because in real world, when we train a model and want to test it later, we usually do not often have the knowledge of the test domain, even unlabeled. So people come up with this domain generalization scenario where we train the model on a collection of source domain data, for example, like a collection of several data sets, and then test the model on yet another domain of data. And so in this case, during the training, we have no knowledge about the test domain. However, this may not be very, very realistic enough. Again, and in one of our previous work, we argue that, okay, if we want to do that, why do we still depend on the partition of those domains during the training time? So in one of our previous work, we basically push the setup to the extreme, that we just train the model on a collection of domain data, collection of domains of data without knowing any sort of partition IDs, and then test it in yet another domains. And this is going to serve as the empirical scope of this talk. So basically for all those experiments, we will test in this setup, although it might be compared to the simpler scenarios in those domain generalization where those methods can still use domain IDs. Okay, there is one common theme across all these scenarios. That is that when we train the model and test it in something else, the test domain is always, in a sense, similar to but different from the train domain. And now let's take a deeper look of this message, like about this similar to but different. So again, let's start with domain adaptation. Basically here, we just call it a study across similar but different domains. And on the empirical end, usually when we study domain adaptation, we train the model on some data sets that are defined by us, and then test on some other data sets also defined by us. For example, we study the domain adaptation from MNIST domain to the street view house number domain, which we study the domain adaptation from ImageNet to its sketched counterpart. And always, I think to a human that it's natural that these domains are similar because they are always about those digits or those image with some primary labels, but different because they are sort of in some different quality. And maybe we can formalize it in the sense that they are different in terms of marginal distribution or even the support of the distribution. But however, in the empirical studies, since we already collect the data set, we can test it. We don't really need to rigorously define what similar but different really means. Okay, now let's come to the theoretical end. Before we talk about this, we need to set up some preliminary background. And that is, in this talk, we want to talk about a standard generalization error bound for almost any supervised machine learning. So basically for supervised machine learning, we talk about this generalization error bound, where we have that the expected error during test is bounded by the empirical error during training, as well as some technical terms regarding hypothesis space, the number of samples, and the probability of this bound holds. So I personally think that this bound can cover almost all the supervised machine learning, in the sense that it basically tells us supervised machine learning is basically an art about designing new hypothesis space or getting new samples, and then we can train it to for a small empirical error during training, and then we can hope for the good predictive performance during test. Okay, with this setup, we can talk about the theoretical understanding of domain adaptation. And unfortunately, even on the theoretical end, the similar but different is barely rigorously defined. So here again, we use one master form to summarize multiple theoretical work regarding the domain adaptation generalization error bound. For example, for at least these 5 papers listed here, they can summarized by this one equation, where basically we append 2 new terms for the standard generalization error bound, where one term is about divergence between distributions and is estimable, and the other term is about the learnable nature of the problem, where it is not estimable. And this theoretical study of domain adaptation has become quite popular. And probably one thing that is more popular than them is the resultant architecture that are inspired by this line of theory. For example, inspired by the first work from Ben David in the domain adaptation theory, this is the domain adversarial neural network. It's basically designed following the theory to the extent as much as it can. It basically talks about that we want small empirical source error, primarily pursued by this blue architecture, and probably also that green one. And also in that paper, they introduced this domain classifier used to guarantee that we have a small divergence term. So even in that paper, they humbly say that this is directly inspired by those theories of domain adaptation, and as much as it can follow those theories, because there are some non-estimable terms in those theories. So this architecture should naturally works very well. However, it does not like so. For example, even in their original paper, they say that the method failed to generalize in certain closely related source target pairs. For example, even the simplest digit classification domain adaptation problem from MNIST to straight host numbers, it does not generalize very well. And then the community come up with try to explain that why this very popular network and also seems to be very theoretical sound network does not work very well. And several line of work come up with this hypothesis about misaligned labeling function. So here is a little more details about this, the hypothesis about misaligned labeling function, and this is taken from that paper listed there. And basically, the main argument is that domain adversarial neural network will not work if the labeling function shifts from training domain to test domain. And here is an example in their paper. Basically, they say that, for example, in the source domain, the left-hand samples are labeled as 0, and then in the target domain, the right-hand samples are labeled as 0. In that sense, even if we use all kinds of tricks to align the marginals of those domains, even after the alignment, we cannot find a simple classifier that can do the job correctly. So basically, this works, and several follow-ups try to argue that one reason for domain adversarial neural network not work is this existence of misaligned of labeling function. However, this does not seem very intuitive, in the sense that a human might prefer that those samples across similar but different domains will have a shared labeling function, right? After all, there is a reason that both of these digits are 2. And for a human can easily recognize that both of these digits are 2, and there should be a reason behind it. And the reason is probably that why these labels are defined as 2, or in those machine learning sense, the labeling function is the same across these 2 images. So basically, motivated by all this background, we try to come up with a new theory regarding domain adaptation, and also try to explain that well, there should be some shared labeling function across this train and test or source and target domains, why something like this still happens. So to do that, our first step is to rigorously define what similar but different really mean. So in our work, this slide is still about the intuitive definition of similar but different. So in our work, we consider those two domains to be similar when there is a shared labeling function across those two domains. However, their two domains are different when the training domain has an additional labeling function. For example, as the example shown on the slides, we try to train a model about triangle versus circles, and also we train it on the source domain and then test on the test target domain. So when we train it, the classifier can easily identify this through ERM, and but it cannot really classify the samples on the target domain very well, even if we align the marginals. However, there exists another labeling function that when the model can learn that, the model can classify the samples over the target domain correctly, even if the marginals are not aligned. Okay, with this setup, we try to formalize it. Basically, in this work, we talk about the study from this data space to the label space. And then for any samples in the data space, there exists a labeling function that maps the sample to that label. And this is also how the label is defined. And however, within the data space, there exists a distribution. Here we call it PS, the S for source. And then for any sample sampled from that distribution, there coincidentally exists another labeling function that maps the sample to the same label. And we use that phi to denote this function. And later we also call it superficial functions. And if someone is not a fan of all those mathematical notations or all these like relationships, just keep in mind that across this talk, that the blue thing always means the superficial thing, that the one we want the model to discard, and the red thing always means the semantic thing that we hope our model to learn. And if it only learns the red thing, the model will be robust. And then the purple thing will be a mixture of these two things. Okay, so if you are not a fan of all those mathematical stuff, just read the colors should be suffice for the rest of the talk. Okay, and then with this setup, we also need to go a little bit deeper about those details about how to measure the functional differences of this, of what we can learn, and also the superficial functions and the semantic function. But these details, I think we can skip for this talk. And then with all those setup, we come up with one of our major results that we give it kind of a cool name, but it's a very intuitive result. Basically, we say that for the generalization error bound of robust machine learning, all we need is to append this C theta term in addition to the standard generalization error bound. And then what is this C theta? It expands like this. Again, it involves those details in the previous slide, but intuitively, it just means that the accuracy gain because our model theta learns that superficial function, the phi thing. And up to this point, when we wonder like, what's the point of all this? So we talk about robust machine learning. We talk about the challenge of the model learns the superficial function, and now all we did is just append a term like, okay, that's the accuracy gain when the model learns that superficial functions. That seems so intuitive and maybe kind of trivial. However, the main message lies in here. So basically, from our results about the generalization error bound, we can see that if we want a robust model, all we need just to guarantee those two terms to be small because the technical terms can be easily controlled before we train. And during training, all we need is to train the model to have small empirical error as well as small C theta. And then how we can get small C theta depends on the knowledge we have, whether the features of those superficial functions or the superficial function itself. We have different methods, and as we will show in the next slide. Here, just want to emphasize that no matter what, whether those features or the function itself, this usually requires some additional domain knowledge of the task. Okay, and then with that setup, let's look at this result. The above basically says that if we have the knowledge about that green thing, the features of those superficial functions, and if we consider an upper bound of c theta, which is introduced in a very simple manner, all we need to do is that fact that the identity function is always smaller than 1. If we consider that upper bound of c theta, then minimizing the empirical loss as well as the upper bound will be mathematically exactly the same as what is known as worst case data augmentation, or in modern days is more popular name that adversarial training, that I think is one of the dominant methods in robust machine learning literature. It's basically about the ideas like perturb those features to maximize the training loss, and then train the model again with those new samples with those perturbed features. And then on another branch, if we have the knowledge of why this is a little bit more complicated, as we need to split the model into encoder and decoder, and then we need an assumption of separation functions, which basically says that, for example, in image classification, the perturbation of image textual background will not change the fact that a dog is a dog. It's I hope it's still an intuitive argument and a reasonable assumption. With these two things, if we minimize the empirical loss as well as this c theta, the term will be mathematically the same as this term listed on the right-hand side. Maybe this looks a little bit more complicated, but if we look at closer, I hope it will ring a bell, because this is actually exactly the optimization algorithm for domain adversarial neural network. It's basically here we show that if we have some additional labels, for example, the domain IDs in domain adversarial neural network or its extensions, then all we need to do is still use the standard hypothesis space, but estimate the parameters with minimizing the loss for those additional labels. That's how we estimate that phi. And then basically, again, for example, corresponding to the previous example, now the phi is that domain classifier. And then we lead to this idea about the machine learning countering those domain-specific IDs, for example, the domain adversarial neural network. And then on the other hand, this also aligns very well to another branch of work. Basically, it talks about the design of that phi model. We can design that hypothesis space according to the data and the task, and then we can estimate the phi with standard loss. And this corresponding to a large branch of machine learning recently, especially in the field of countering what's so-called Bayes signal or spirit signal or against superficial signal confounding factors with a design model of Bayes. For example, the most popular one will be counter the background, the texture, or like little patches of those images. So and with this setup, this is a quick recap. So basically, we introduced this principled understanding, and then with the principled understanding, we argue that all we need to do is to optimize for small empirical loss and small c theta term. And with that, this corresponds to several methods, including this worst case data augmentation method, or more popular known as adversarial training. And of course, it could correspond to regular data augmentation, where we can further improve its efficiency by some what we call alignment regularization that will be introduced later. And then for another branch, it corresponding to the entire branch of methods about regularizing hypothesis space, and it falls into two scopes, where we have the functional space of the environments corresponds to the works countering superficial space features, or we have those label space of environments corresponds to those works use additional classifier to introduce environments, for example, domain adversarial neural network. And also there is a third line, we didn't include it in the slides because it will require more assumptions. So basically, it also a little twisting of these terms, it will be also corresponds to the worst case sample rerouting method, with the most popular example probably as the group DRO family of methods. And essentially it's basically about reweighting those samples with learned functions so that the model pays more attention to those samples that introduce an increased loss. Okay, so this is the second part about the principled understanding. So now we can probably move on to the third part. Now how we can leverage those ideas to introduce some new methods. I don't know if I should pause for some questions. Or maybe we can move on. Okay, so for the next part, we basically motivated the example again.
Basically, I see caught some questions.
Sure. Yeah, so basically we motivated the challenge again by saying that the challenge of robust machine learning lies in the learning of correct features. For example, we list this example here as if we want to build a classifier of sea turtles versus tortoise, if we collect from, for example, Google Images, the model of sea turtles will mostly have that blue background. And if we train a model like that, it will probably consider the right-hand image as the sea turtle, although that's actually a tortoise visiting the sea. Okay, so this is probably a standard example in the literature about robust, especially about contouring those spurious or best feature literature. Okay, with that setup, so let's take a look at existing solutions of that line of research about contouring spurious features or best features. And one very popular branch of work is about worst case data augmentation or linear data augmentation. And it usually requires some specific knowledge about how to augment data to introduce invariance. And then, of course, since it's data augmentation, after we augment the data, we just train the models. The other side is about regularizing hypothesis space, and it's basically about the idea that according to the task, for example, whether we want to counter texture, we want to counter background, we just design a smaller model that only learns texture or only learns the background, and then we regularize the entire model to learn something is different from what the smaller model learns. And of course, as expected, this requires some specific knowledge about what we want to be invariant. And here, since this two line of research follows the same builds upon the same ground of the principled understanding, then we just ask a very, very simple and natural question that since they are from the same family, actually, why not just put them together? So together in that work, we introduce a very simple heuristic. We just put these things together and we call it a worst case data augmentation with regularizations. And in that work, we use some generic data augmentations through those frequency domain. And that's kind of remove those dependency on the prior knowledge of this task. And then we use some worst case selection from the choices of the radius of those frequency domain. And then in addition to that data augmentation, we simply borrow the right-hand idea, introduce an additional classifier to regularize the learned embeddings to be the same across these two domains. And of course, since the augmentation naturally offers a set of labels for the domains, right? The original versus augment. This simple idea comes to work pretty well. Maybe as expected, since it's in integration of two different methods from the same family. And here is one screenshot of the results we get. And here this is the methods from the regularization family, and these are the methods from the data augmentation family. And and here are our new method together with the ablation study, as we can see here, it stands out. Okay. So this concludes the first paper, and then we try to ask that, do we really need that classifier? For example, again, we use this figure just as a generic example of the model architecture family of the architecture of that entire family basically is about an additional classifier despite how it's designed to introduce some invariance. We try to argue that we try to ask the question that is that so necessary to introduce this classifier, or maybe its extensions in those more modern works. Since this classifier or the extensions are there only to push the embeddings to be invariant for those two domains. And it is not so necessary if we have more efficient methods, especially in the data augmentation settings where those data augmentation will naturally introduce two sets of domains, right? The ones of the original and the ones that are augmented. So following this thought in another piece of work that listed below, we try to argue that maybe we don't necessarily need a classifier since those we have very natural one-to-one correspondence between one sample and its augmented counterpart. And then we introduce this idea about alignment regularization, or maybe more popular known as consistency regularization or consistency loss, to push the model to learn the same representations from an image and its augmented counterpart. And so this idea is not introduced by us, since there is plenty of works using this kind of regularization, especially together with data augmentation. For example, here are some examples here. For example, the L2 distance and cosine similarities for speech recognition, the squared L2 distance for adversarial robust vision models, and KL divergence for, again, adversarial, and also Jason-Shannon divergence for those textual invariant image classification, and many, many others. And so at this point, we want to ask another question, like if there are so many methods out there about the distance metric and where those distance is applied, we want to ask whether there is a general method that can work well across all these applications, and hopefully it can also enjoy some theoretical support. So here for this talk, I just skip all the details we did to identify this method. We basically run a large track of experiments to test them, and also we offer a little bit theoretical proof about those identified methods. So at last, our results indicate that the squared L2 norm is probably one of the most favorable choice as the regularization when we use together for domain adaptation, together with data augmentation to introduce the invariance. And with this setup, we start to compare whether our method, despite its such a simplicity, can compare with those advanced methods. So basically, we experiment in 3 different tasks, namely the rotation invariant classification, the texture perturbed image classification, and the cross-domain image classification. And for each of these tasks, we compare to the top performing methods specially designed for one of these 3 tasks. For example, when we talk about rotation invariant classification, we compete methods that are specially designed to be rotation invariant, whether they can be texture perturbed invariant or they can generalize cross domains. We don't know about that. And even in this sense, our methods, despite its simplicity, can compete with those methods. And in addition, it uses the same generic approach across these testings, and the augmentation functions are the same as the synthetic experiment. So here we show that some bars of the results, and the ones with the line under it are the methods we introduced. And here, basically, we show that the simple method we identified can even compete with the top performing method that are specially designed for each task, which we consider is a strong message. Also, we consider as a evidence for the usefulness, maybe of our principled understanding. And for more results, it's listed in the paper on the slide. Okay, and then with that, we can move on to the very last branch of this work, which is also a new method we introduced, and also in a very, very simple manner. So here again, we talk about robust machine learning in the domain generalization sense. And here is a reminder of the domain generalization, where basically we can train the models on a collection of domains and then test the model on yet another domain. And here this is a very popular data set called PAX. As an example to show here, we can train the model with images across sketch, cartoon, and art painting, and then test it on photos. So again, we use our method in the sense that during training, we don't consider those partitions of domain IDs, but since we compete to those methods that are using those, some of them are using those IDs, we just list it as under the domain generalization umbrella anyway. And along these years, the community achieved several very encouraging performances about the about domain generalization on multiple benchmarks. And more recently, there is a challenge paper regarding, in the sense that whether those domain generalization methods are making sense, as the paper listed there. And they show that the developed domain generalization methods cannot perform well once taking the average performance across a large set of hyperparameters, and ERM is the best in comparison to the average performances. Okay, so that's kind of raise an alarm for development of domain generalization. And however, we at least we don't really take this work very in a very negative way. For example, there are several counterpoints we can make. First one is that all the methods probably will fail if we take the average performance across large set of hyperparameters anyway. Even the ERM will probably fail if we consider the hyperparameters of learning rate from maybe 1 to the minus of 12 to 1 to the 12. 10 to 12. Okay, another argument is that many of these methods are actually extensions of ERM. So it probably should be at least as good as ERM. Okay, and there is also another paper show that do we really have a loss of domain generalization? And if we consider there is a loss, it's probably we didn't take a look at the data set that is close enough. For example, in their paper, they argue that there are 2 kinds of shift in that data set, and they call it they list that the list that 2 shifts as in diversity shift as well as correlation shift, which I think is mostly about the shift of the support of those samples or the density of that samples. And if they argue in that paper, they show that if we looked at this data at this higher granularity with more details, those design methods actually can outperform ERM. For example, if they test the methods on those 2 different sets, one is a diversity shift set, the other is the correlation shift set, we can show that for each of set, there is a couple methods that can outperform ERM. And if we look closer on the diversity shift data set, the top performing one is, by the way, also from us, is essentially a worst case data augmentation method. And in the sense of it's an extension of ERM by basically just perturbing the samples features during training. And it performs the best on the diversity shift leaderboard, but not so well on the correlation shift one. And then on the correlation shift one, the top performing methods, if we look closer, they're actually a worst case sample reverting family. They're actually from the worst case sample reverting family methods. And I hope we still remember that both of these methods are some, we can show that there are some extensions about our principled understanding with some assumptions introduced. And at this moment, I think it's the idea to introduce a method that hopefully can do well in both of these 2 branches will lead to will have a very promising direction about how to introduce the method that can do well in both directions. So again, since both of these methods are from the same principled understanding, so here we talk about the 2 dimensions of these ideas. Imagine this is just a NumPy array of the samples that we fit into our deep learning model. Then along the feature dimension, we can introduce this worst case data augmentation family. It's basically about perturbing the features that once considered predictive by the model, and then use perturbation to construct data that are harder for the model to learn. And then on the other dimension, we can do a very similar stuff. It's about weighting those samples that are harder for the class for the model to pay more attention. And then since both of these methods have a very has a very shared concept behind it, and also it linked with our principled understanding. And again, we just asked the question like, why not just put them together? So and we just use this simple heuristic to put these things together, and we call it worst case along the 2 dimensions and the W2D method. And here are some more details about it and the algorithm listed there. And so with that, here are some results of our W2D method. And again, if we evaluate across those diversity shift and the correlation shift, we can show that on the diversity shift, that W2D method will, of course, list as the top position because it naturally inherits the power of that RC method, which is the worst case data augmentation on the sample dimension. And then on the correlation shift is again at the top position, although it's a tie, by inheriting the power of the worst case sample revealing methods. I think one reason that the method does not perform at the very top is that we only use the most generic idea on the sample revealing set, not as fancy as this top listing VREX method. So it probably has some challenge to outperform that in those numbers, and also which also introduce those opportunities. But nonetheless, it's still listed as a tie of those top methods if we talk about the ranking score, which is introduced as probably a more general evaluation metrics by the original paper who proposed these 2 kind of looks of data sets. Okay, with that, this is actually the last page of the slide. So yeah, so that's all of the stuff I presented. And so thank you very much for your attention. And again, just a recap of the major contributions that we introduce a principled understanding of robust machine learning, which involves a new generalization error bound from the data perspective. And I think the significant message is that generalization error bound naturally connects to the existing literature. And then with that principled understanding, we introduce several new empirical methods for robust machine learning. I hope one may have that question like, why this introduction of new methods sounds so easy and maybe trivial, since it's mostly about the combination of existing methods. And I think that's the point we want to make here. So basically, because of the principled understanding, we notice that all those methods are actually from the same family. And there exists a very natural way to just put them together. And so also because of the natural principled understanding, this integration of methods look very, very easy and straightforward. Yeah. So that's all I have. Thank you very much.
Thank you very much. I think there's one question in the chat box.
Yeah, sure. So the question is the L2 regularization used as the consistent loss similar to SSL? Yeah. Yes. So again, we didn't intend to claim the novelty of using that regularization, L2 regularization, but our point is we noticed that L2 is probably one of the most favorable one across all those choices about distance metric. So basically, essentially, it's just any distance we can optimize, right? And our main message is that the L2 seems to be one of the best performing methods, but we only test that in supervised learning sets. We didn't really test in SSL. Yeah. Yeah. Thanks. Another question is the second question is how do you come up with the principled understanding to show the new generalization bound? Yeah, I think sorry. Yeah, I think we are motivated by these challenges. Here, basically, there are some challenge about the robust machine learning and also some explanations. But we don't really want to settle with these explanations because we think they are not very natural. And with the argument here that I think the labeling function there should exist the labeling function shared across them. And then we basically try to design it following that path. This is a wonderful question, and the question is like how this connect to the certifiable robustness studies, for example, randomized smoothing. This is a great question. We don't really have a formal answer at this moment. But a conjecture is that the randomness smoothing, as its name implies, is it covers a large space about what the perturbation of those samples can see. So I didn't really present this page. Yeah, I didn't really present this page, but this here also involves a perturbation of the space of the possible perturbation and the actual perturbation on what features can be perturbed. So I think there could be a connection there, but in our work, we haven't really drawn the connection yet.
All right. We really appreciate Dr. Wang's give us talk. Since there are no further questions coming up, this is the end of our today's seminar. Again, thank you, Hao Han.
Sure. Thank you very much for the invitation and thanks for all this.
Okay. Bye-bye.
Bye.